Hi, my name is Aniek Eerdekens. Today I will present my work to you on resampling and data augmentation for equines behavior classification based on wearable sensor accelerometer data using a convolutional neural network. $15 million. That was the sale price of the horse in this picture. Although this is an exception, the financial and emotional involvement of horse owners makes them want to know about their horse's health and welfare. Detecting horse behavior is a first step towards this goal. In this study, we evaluate a machine learning model to classify accelerometer data on 3 criteria. It is the accuracy, the classification time, and the generalizing capabilities of our designed model. In order to reduce the classification time, sampling rate reduction is performed. To test the model robustness, various data augmentation techniques such as jittering and rotation are applied, and the model is evaluated on different horse types. First, I will present the methodology used in this study, followed by the results in terms of accuracy and classification times. Finally, I will draw conclusions and share with you my vision on future work based on the work achieved in this study. Measurements are performed on a variety of subjects, like a sport horse, a Frisian horse, and a pony. They have a difference in height, condition, and shoeing. The lame horse and the pony are interesting to validate the model on, since lame horses have asymmetrical gait patterns because they consistently shorten the cranial or forward face of the strides. And the pony has higher mean acceleration values for the gaits trot and walk. So we can see if the model still performs well on those types of data. To collect data, 2 Axivity AX3 accelerometers are attached to the lateral side of the tendon boots, as you can see here. Sensor data is gathered at 50 Hz. Measurements are done on different undergrounds, such as sand mixed with geopath polyflakes, a hard underground, and meadow. Also, a difference is made between wet and dry sands. The horses were exercised in 2 ways. They were either ridden or launched. In this study, 7 behaviors are detected. First, the natural gaits of a horse: stand, walk, trot, and canter. Then we also detected 3 other behaviors related to colic. Colic is the most common emergency in equine practice, with approximately 4 out of every 100 horses having an episode of colic each year. When a horse is experiencing an episode of colic, it is showing one or a combination of the following signs of pain. When a mare is ready to give birth, she will show signs resembling those of colic. We detected flank watching, pawing, and rolling. Data from 6 subjects was gathered. When looking at the distribution of the measured activities, we can see that the share of the abnormal behaviors is lower. Therefore, class rate adjustment is done, since otherwise machine learning algorithms will be biased towards the majority group and risk not to perform well on the classification of the minority classes. This figure shows the used multi-layer convolutional network with 2 convolutional layers, which are followed by 2 fully connected layers. The output of the last fully connected layer is fed to a 7-way softmax layer, containing the softmax activation function to introduce nonlinear properties to the neural network. This layer produces a distribution over the 7 class labels: stand, walk, trot, canter, roll, paw, and flank watching. The first convolutional layer filters the input accelerometer data with 64 kernels of size 3 × 1. The first convolutional layer is then followed by a zero padding and a max pooling operation. The second convolutional layer takes as the input the pooled output of the first convolutional layer and filters it with 16 kernels of size 5 times 2. Hi! Now I will show the results in terms of accuracy and classification times, and I will draw conclusions and share with you my vision on the future work. Existing data was measured at 50 Hz and was resampled to lower sampling rates. It is 5 Hz, 10 Hz, 12.5 Hz and 25 Hz. The performance of the model improves from an average accuracy of 99.61% at a sampling rate of 50 Hz to a maximum average accuracy of 99.74% at a sampling rate of 25 Hz. The average accuracy of the model decreased with about 0.42% when the sampling rate was reduced from 25 Hz to 5 Hz. The classification time per sample is increasing 16-fold from 5 Hz to 50 Hz, since the computational complexity increases. When taking a closer look at the exemplar confusion matrices of the validation data, we can see one misclassification of trot, one misclassification of roll, and one or two misclassifications of flank watching are occurring. Gaussian noise is added to the training data, validation data, and both, with a standard deviation between 0.1 and 1. Still high accuracies are reached for the 3 cases when a noise of 0.3 standard deviations or smaller is added to the signal. A fast decline in accuracy can be noticed after adding more than 0.3 standard deviations of noise to the validation sets. The classification time per sample when noise is added is in the same order of magnitude compared to when no noise is added. Results on rotation. Accelerometer data is rotated along one of the x, y or z axis with an angle from 0 degrees to 180 degrees. Those rotations are applied to the training set, the validation set and both. The model accuracy increases on average with 0.32% when applying a 10-degree x, y or z rotation to the validation or training set. The accuracy decreases faster when rotating around the z-axis for rotations of the training sets. The accuracy decreases faster when rotating around the y-axis for rotations of the validation sets. When rotations are applied to the training and validation set simultaneously, the baseline accuracy of 99.61% is in many cases exceeded, with an average of 99.69%. The average classification time per sample is in the same order of magnitude than when no rotations are added. Hi, my name is Annick Eerdekens. Today, for validating the model on unseen data, the model is trained on 5 horses and validated on 1 horse. This validation is only done for the gaits, since not every horse performed every activity. Horse 1, 2, 4 and 5 reach all accuracies above or equal to the baseline accuracy of 99.61%. Validation of the model on horse 3 and 6 are performing the least. And this is in line with the expectation, since horse 3 is the lame horse and horse 6 is the pony. The classification time is on average 402 microseconds. Conclusion. High accuracies and short classification times are reached at small sampling rates. Since a convolutional neural network is used, no feature engineering is necessary. The proposed algorithm can be applied to not only different subjects, but can also be used at lower sampling rates and with different measurement disturbances such as noise and sensor rotation. For the future work, we will add new behaviors to the training and test set. We will perform energy measurements on embedded devices. We will calculate metrics such as the number of strides, the velocity and the stride length, etc. And we will validate other machine learning models on our datasets. Acknowledgements. This work was executed within the IMEC Icon HoofMate project. Thank you for listening, and are there any questions?